All right. So cool. Okay. So this is our second week of FTC programming. So hopefully we have a lot of people that were here last week. If it's your first time coming to one of our camps, this is STEMpump Online. My name's Ritesh, and I'm gonna be leading you through the camp. So who are we? STEMpump is a student-led initiative that teaches students the best of STEM technologies for free. We cover everything from programming to robotics, even game design. So, being a part of the pandemic and all these quarantine that's going on, we decided to take a shift from our in-person camps that we usually do in Dallas, Texas. Hopefully, we have some of you that have attended, to a more online focus where we've been teaching 2 to 3 camps every week covering a variety of topics. And this camp, the FTC programming camp, is a 3-week camp. So every Tuesday from 3 to 5 we'll be meeting and just kind of going over each week, and it builds on each other. So get this pointer. So like I said, each camp builds off the one before it. So FTC programming is on these days. So May 26th, which was last week, June 2nd, which is today, and then June 9th next week from 3 to 5. So during the stream, feel free to ask questions in the chat. We'll get around to answering them. We have some people in the chat answering your questions while this is going on, so we don't get bogged down in them. And as it normally goes, if you don't finish something today, we'll pick it up next week. And so each one of these camps builds on each other, but we're going to do a little bit of a review before we kind of get into the new stuff. So overall camp topics, we have the basics of Java, we have op modes and op mode design, we have teleops, we have autonomous with linear and iterative, and we're going to kind of go over what all these are. We're going to talk about sensors, so the main 3, touch, color, and distance. We're going to talk about version control, something we like to call a dynamic workflow, encoders and gyro basics, as well as vision basics. So last week we got the basics of Java covered, op modes, and then teleop. And then today we're going to be starting off with our autonomous and go through sensors, a little bit of our dynamic workflow and modular code, as well as encoder basics, with next week for the version control, vision basics. So originally we said that we were going to go talking about how to do virtual robot building today, but we're going to make that into a separate video that we're going to post on YouTube because it's kind of out there, and it also just doesn't it kind of messes with our system on how we have it right now. So we're going to go straight into making autonomous today, right before, just double checking something really quickly. Okay, cool, yeah. So last week we ended on making our Mecanum code, which was a 4-wheel drive where each of the wheels kind of slant inwards, and we kind of talked about how we map each one of those wheels. We set directions to the motors on each side of the drive. We do telemetry updates, and then how do we correspond those to the controllers. And then we also did the same thing with a 2-motor drive, talking about how we can do an arm using triggers right here. How do we use a servo with buttons, and set position, where we can change the position of the servo. We talked about how to set power. Like I said, we talked about telemetry. We talked about using linear op mode, and then we also looked into the iterative op mode, otherwise known as just op mode. And it's pretty much the same, except it's broken down into more different types of functions, and that we're going to talk about today, which is a large part of today, which is talking about functions, methods, classes, and objects, and how we can avoid repetitive code over time. And then kind of going through this. So if you weren't here last week, we'll kind of do a quick review. So to start autonomous programming, we're only going to be using a linear op mode today. Next week, we're going to talk about the usages of iterative op modes and a autonomous. So a state machine is what it's called, and we're going to kind of go through the theory behind that, how it operates, and then how you can integrate it into your robot. But first, we're going to do a little quick Java review. So here are some of the 3 main variable types that we talked about last week. So we've got integers, doubles, and booleans. So integers are 1, 2, 3, -1, 5, -89. So basically any numbers that don't have decimals at the end. They can be positive or negative. Talk about doubles. So doubles are basically most numbers that have a decimal at the end and then get pretty precise. So I think it's a pretty long amount that they can do. We did talk about the float, but most of the time you're going to want to use double over the float just because it's easier and you don't have to worry about the numbers rounding if you get super precise. We talked about booleans. So boolean is a true false value. So it's 1 or 0, yes or no. And then those evaluate conditions for if else statements. So if 4 is less than 6, that's true. So before we kind of do a quick demo of all the things that we did last week and are going to talk about this week, we're going to introduce 2 more topics right now. So we're talking about while loops. So a while loop runs as long as the condition that we set is true rather than the if statement which only runs once. We'll be using while loops a lot today as a part of, making sure that things repeat over and over and over again until, the condition that we set is false. So if we look right here, we set an integer a to 0. And then we say while a is less than 10, so 0 is less than 10, we want to print a, there should be a capital S, we're going to print the value of a, and then we're going to add 1 to a. So a plus plus is the same as adding 1 to a. So it's the same as writing a equals a plus 1. And then for loops run for a certain number of times. So the while loop, we can run it, there's not really a set amount. Right here we do have a set amount. It's going to run, 10 times from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 times. But most of the time you won't really need to do that. And as you can see right here, we actually used the while loop last week when we were talking about while op mode is active. So while op mode is active is a function that returns a value that's true or false. And you might not understand what that means now, because we're going to kind of go into it later today. But basically what it's saying is while this program is being run, then it's going to continue through having running the code over and over again rather than running it one at a time like an autonomous might, because by looping it then we make sure that we're always sending the same feedback back to the robot. So right here, like I said, it'll run basically this will run 10 times, but you might as well use a for loop. However, while loops are a lot more common in FTC than for loops are. So a for loop runs for a certain number of times rather than the while loop, which runs as long as the condition is true. And this loop isn't run as much in FTC. So to call this, we'll just do for, and then right here inside the parentheses, we're going to create an integer named I that is equal to 0, semicolon. Then we're going to say as long as I is less than 10. So we're basically going to say we're going to run it 10 times. Like I said, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 times. You could change it to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 by either making this a greater less than or equals, or just making this 11 and making that 1. And then right here we're going to say what we're going to do for every run through the code. So for every loop, we're going to add 1 to I. So it's going to print out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But it's not going to post 10 because it has to be less than 10. So let's just kind of look at some of these. So let's create an integer. So an int of, we're just going to call it whole equals 17. We're going to create a double. We're going to call it pi 3.14159265. We're going to create a boolean of apple equals true. And you don't really need to you don't have to follow on with what I'm doing. This is just kind of a review. So we're going to create our first if statement right here. So if whole is less than 20, we're going to print out whole and then we're going to do plus is less than 20. And so this whole plus is basically saying let's put the number right here, so 17 is less than 20. So if I hit execute right here, oh, that's weird, what is happening? Just reload the page. If it loads. Come on. Okay, while we're waiting for that to load, I'll kind of go through some parts of Auton while we're waiting for that to load. So in the parts of Autonomous, there are lots of different ways to program. So there's a lot of different parts, and here are just a few of them, and we're going to go over a few of these. But most autonomous programs will use most of these parts to make sure their autonomous is as accurate as possible. So all of these parts in the bold, so the time, sensor, encoders, gyro, and vision are the ones we're going to cover. We're not going to cover odometry because of how complex it is, and what you need is a lot of hardware focus on it, and we don't have access to that. But let's see, did that load? No. It's terrible. So we're going to talk about time today, sensors and encoders, and then gyro and vision next week. So most teams, especially us last year, we used time, sensors, encoders, gyro, and vision. So we used the entire thing. Most parts except odometry because it was getting pretty late in the season. And then we can guarantee that we have a lot of backups in place if something doesn't work. So like the sensors would be helpful to making sure that we're on the right part of the field. Time would be helpful if we want to make sure we're within 30 seconds. Gyro is helpful when using mechanisms because there's a slight drift to it. So the gyro helps reaccount you for your angles. Encoders to make sure we're going the correct distance, and then vision for finding the sky stone at the beginning of a match. So here's kind of a review on the types of op modes. So we have the iterative op mode, otherwise known just as an op mode. And we kind of looked at this already right here. Right here. So in iterative op mode, there's a loop method, which is called repeatedly throughout the operation, so it's just going to run it over and over and over again. And op basically stands for operational, so it's an operational mode, and it's basically how we're going to program either our autonomous or TeleOp programs. So our loop method is called repeatedly throughout the operation, so it's going to run over and over and over again. So we had our while op mode is still active. This loop does the exact same thing. So the op mode runs code through the loop and other methods the entire time it is on. It is helpful for TeleOp, but harder for autonomous. Like I said, so we only are going to go over the linear portion of autonomous today with the state machine for next week, because that takes a lot of time to go over and conceptualize as well as plan out. So the iterative op mode isn't recommended for beginners as much, because it requires a lot more focus on looping and understanding how methods and functions work, which is why we're saving that for last. And then the other one, which you're probably more familiar with, is the linear op mode. So it's a linear way to program, meaning it goes one step at a time. So if you're thinking about, making a sandwich, and you'd program it like walk over to the table, open the bread bag. So it's very linear, one step at a time, versus the loop, which is just going to run it over and over and over again. And you could technically do the same thing right here, but in autonomous, there's no really point of looping through the same actions over and over again unless you have very good reason. Like, you don't want to go get a sky stone, get both sky stones, and then repeat the code to get sky stones that aren't there anymore. So it's a linear way to program. It goes through one thing at a time, and then once all the tasks are completed linearly, the op mode ends. And it's easier to understand for beginners, and a lot of the teams just use it because it's very easy to go through. So it's helpful for both autonomous and TeleOp, because in autonomous you can go one by one, and even in TeleOp you can just use the while op mode as active, and we're going to kind of talk about that a little bit more today as well. That load? Okay, cool, this loaded. So let's see. execute. What is it doing? Execute. I think this website's just broken. So first, we're going to create a program today that drives the robot in a square. So this might not work for each of your robots if you try pasting this code directly in, because every robot has a different drive configuration with different variables such as wheels, gearing, power, and weight, influencing how the turns work. So to do this, you should already have Android Studio open, and I recommend that if this is your first camp, I suggest watching the YouTube video that we posted, and you can go to that at stempump.com/r/YT, and you can watch FTC Programming 1, which we recorded last week. Is this your first time to kind of go through the process of understanding each one of these parts, one at a time. So first, you're going to make a new file inside here. So we're just going to right click, new Java class, and we're just going to name it my first auton l.java. Or we're going to say that. Yeah, it should figure it out. Okay, and so right here, first what we're going to do is we're going to write extends linear op mode. This way, the code knows that it's building off of a linear op mode, and this is Android Studio. A lot of you guys that are new may have used OnBot, but we're going to kind of get you introduced into Android Studio because it's a lot more helpful for integrating, different types of packages and more, freedom and finesse with this. And then we're going to write @autonomous, and if you see how this is, and it says press enter to insert, you can hit enter, and it auto does most of the code for you. So you can hit name, and we're just going to name it my first auton L. And we're still getting errors right here, so we're going to continue this. So before we actually call any motors or any of the hardware, we're going to write @override, and we're going to write public void run op mode. And this, now all our errors are gone. So the reason we override is because linear op mode already has its own run op mode method. So overriding it means that we're going to put our own code into it. And that's basically all we really need. So let's start creating some of our motors right now. So you can do DC motor left drive, right drive. And this is the same as writing DC motor left drive, DC motor right drive. Next, we're going to create an elapsed time object, and we're going to kind of talk about more what objects are today. But this is just kind of understanding how the time works. So we're going to make an elapsed time object named runtime equals new elapsed time. It sounds super redundant, but it's going to make a lot more sense today when we kind of create two of our own objects, one for the robot and one for our movement. Next, we're going to create a double of power. So we're going to say double power equals 0.85. And so power operates on a scale from 0 to 1. And that is the exact same as 0% to 100%. So 0.85 is really the same as 85%. So that kind of gives you a scope. If you type in 85 as your power, the code will recognize that as 1, because anything higher than 1, it will drop down to 100%. But it's more better so you can do this and you can understand how power fluctuates and all that. So right here, instead of our run op mode, we're going to actually declare some hardware maps, which tell the robot, this motor I'm linking up to the other motor. And yeah, I can go a little bit slower. So we have our left drive right here. And so what we're going to do is we're going to say hardware map dot get. So we're going to say, okay, find me a certain type. So we're going to set this motor is equal to DC motor dot class, and we're just going to name it left underscore drive. So what this basically says is that we say we have a variable of DC motor. So this is our virtual version of our motor, and we're going to call it left drive. And we're going to say connect this variable to the one that's actually on my robot. So for those of you guys that know, you have something called a driver station and a robot controller. and those are 2 Android phones that you can actually custom configure your robot. So inside the configuration, you can write what motor is called left_drive, and this way the code can say, okay, so if the phone tells me it's left_drive, that means it's actually, I'm talking about this motor. And that applies to mostly all hardware. So we're gonna do another one. So right drive.get DC motor.class, and we do right_drive. And so now what we're gonna do is we're gonna set directions. So directions, so if you have your motor, it goes one way. But so we have that for our left, and our left motor usually goes the correct way. It moves forward it moves away from us. But when we rotate the motor around for the right side, it moves towards us. So what we want to do is we want to reverse it, so then we move forward, and we're not turning because the motors are going out the opposite direction. So we're going to set left drive.set direction DC motor.direction.forward. And you don't really need to do that, but I kind of like doing it because it kind of gives you a better look at how each one of the motors is interacting with the direction. And I just copy and pasted that, and we have reverse. So that way we can make sure that both of the motors are moving in the correct way when we want to go forward. And otherwise, your robot's just going to, when you want to go forward, your robot's just going to keep turning because both the motors are going in opposite directions. And then next, let's just call some telemetry. And remember, telemetry is a way of showing information back to the drivers. So we can write robot ready. So in this example, we are using a 2-wheel, but you could use this exact same thing for a mechanism drive. And I can kind of show how that works in later once we create our functions to do it. But for now, we're just going to focus on this. So you have telemetry.update. So right here we have our add line. And basically what this does is inside these quotes, we state, okay, our robot is ready. And this is a string. And a string is just any part of text that can't be manipulated, like numbers or like integers or doubles can be. So this is basically any text. We're just going to say robot ready so that the drivers know when to hit start on their driver station after it sets up all this. And we're going to wait for start. So after this, everything that happens after this code will happen as soon as you hit start. So what we're going to do is we're going to hit runtime, or if you don't even need that, let's just go straight into it. So we're going to do left drive.set power. We're going to do power. So it's basically just set my left drive to 85%. We're also going to set my right drive to 85%. And remember, we're making a square. So square, how that works is we're going to move forward, and then we're going to make a left turn, and then we're going to turn left, and then move forward, turn left, and then move forward, turn left, and then move forward. So it makes a square. So we're going to copy the same thing 4 times. So right here we have this. But if we just wrote that, it will move for as long as it does, as long as this op mode is running. So what we're going to do is we're going to add something called sleep. And so sleep, how that works is it basically tells it how many milliseconds long do you want this to run. And do you see how it says long? So long is another type of variable. Like we talked about integers and doubles. Well, a long is basically a more powerful integer as it can hold more value, a larger value than integers can. So right here, we're going to set it for 0.7 seconds. So we're just trying 700 milliseconds. So 700 milliseconds is the same as 0.7 seconds. And yes, you can write your, this is also appropriate. You can write them both ways. Neither way is wrong. I just like writing this way because it's a lot easier for me to read. So left drive hardware map.get DC motor like this. And yeah, there's a lot of like redundancies and a lot of things that first is done, so you can write both ways. So right here, we're going to do left drive set power. So this is going to run for 0.7 seconds. So it's going to go straight for 0.7 seconds. So now what we're going to do is we're going to make sure, well, let me actually just comment that out really quickly. Go forward for 0.7 seconds. Next, we're going to make a turn. So go turn left for 0.3 seconds. And like I said, these sleeping values are going to change based on your robot's weight, its size, the wheel type. So there's a lot of different variables, but understanding, how it works conceptually is going to really help you if you want to copy this code for your robot in the future. So what we're going to do is we're going to set left drive dot set power, and instead of our normal power, we're going to set it to a negative power. And then our right drive, we're going to set to a positive power. So just power. And then we're going to do sleep 300. So what does this do? So to turn left, we need to make sure that our left drive is moving backwards and our right drive is moving forwards. That way we can create the turn of the robot. And then the reason we're going to set it for a less amount of time is because when we're turning, we want to make sure it's less so we get that perfect 90-degree angle. And it's, like I said, it's going to be different based on your robot. But just understanding that you can negate the power to make it go in the opposite direction is really important. So now we have this. So we're going to loop this 4 times. So we're just going to copy and paste it. 1. So this is our first forward and turn, forward turn, forward turn, and then forward turn. And then at the end, we're just going to set left drive dot set power to 0 and right drive dot set power to 0. So right here we have a basic program, a linear op mode, that kind of goes through and it drives the robot in a square back to its original position. So that's really helpful because maybe you just want to drive your robot as a square to park rather than just driving straight. You want to show off. So maybe this is the way you're going to do it. And so at the end, what we did is we declared a set power of 0 just so we made sure that the robot was stopping and nothing else would happen afterwards. Yeah, I don't think this is even working anymore. Yeah, this website broke on my end. So these programs control the motors by controlling the time for each motor. But time is connected to power. So the motors will move faster for the same amount of time at a higher battery than a lower battery. So that's why I don't recommend using time by itself, but combining it with, sensors and stuff like that. So, like I said, so if you are testing your robot with time, right, and it's running perfectly every time, right, and you're at, 12, 11 volts, and then the next day you come back to go work on your robot, you charge your batteries overnight, it's at 14, 15. If you run the code, it will not be anywhere near the same under time. The time is staying the same, but there's more juice in the battery that's going to run a lot faster, and it's not going to be able to do. And then you're going to change your code to be slower, so then you can run through the code. But then the next day, you forgot to charge. You're at 11 volts, right? Then your robot's going to run way too slow. So that's why you don't want to be only using time. You want to maybe connect it with some sensors. That way you can make sure that you have input from the field rather than tracking preset values. And this is what we did this year. So we put distance sensors on our robot that would track the view marks on the field. If you guys had these little pictures along the sides. And then from there we can be able to track, are we a foot away from the sides? Are we 10 inches away, 5 inches? So it's kind of setting up, how far are we? And it's better than using time because then we can use that information to basically influence what our robot does. So we're going to talk about sensors now. So a sensor is a device that detects and responds to some type of input from the physical environment. In FTC, there are various types of sensors that give your robot more information about his environment and then adapt based on those results. So here are some examples of sensors in FTC, and these are some of them that Rev offers. So Rev Robotics, one of the FTC providers that you can get parts and electronics from. So we're going to use, there's the 2-meter distance sensor, there's a color sensor, a touch sensor, a potentiometer, and a magnetic limit. We're only going to focus on these 3 because they're the most commonly used, but we're going to show you how to find examples for the bottom 2. And like I said, these are the 3. So we're going to focus on the 2-meter distance sensor, the color sensor version 3, and then the touch sensor. So the Rev Robotics 2-meter distance sensor measures distance up to, 2 meters with millimeter resolution. So unlike other sensors that have, it relies on the intensity of reflected light, that's how it figures out, how the distance, it's basically checking reflections, which is why it's really hard to use distance sensors against the plexiglass along the side, which is why we used to get into the view marks, because at least there's something solid and nothing's clear that light can reflect and bounce back. So this sensor has something called time of flight, which basically allows it to also track how long it takes for the light to bounce back, which is called, time of flight. And this is actually going to be seen on, the newest iPad Pro when they're doing, augmented reality. This is being used on the new Samsung S20s that were announced. Well, not new, but recent. The new iPhone 12 is going to have one of these things. So it's super helpful for, tracking distance and, with augmented reality. But right here, you see a real life example for the distance sensor. So the time of flight really allows for a more accurate measurement that's independent of the target's reflectance. And this is what it looks like. It's pretty easy. You just plug it in, ready to go, connected. Then we have the color sensor. So this sensor can be used to read and compare colors. It has a built-in IR sensor and a white LED for active target lighting, and it's helpful for tracking RGBA values. So an IR optical proximity sensor is basically, it's an infrared light basically that's tracking, infrared away from, color. So your TV remote has this actually, so it can interact with the TV. It sends an IR beam, which which isn't visible to the eye, so it can communicate with the TV. And then there's a little white LED that switches on the back right here that you can turn on, which I recommend, because then it floods the environment to make sure that no outside light really influences your values, and sometimes if it's close enough you don't need it. And it's helpful for tracking RGBA values. So RGBA stands for red, green, blue, and alpha. So alpha is really, an opacity type thing. So 0 alpha means it's completely transparent, 1 means it's not transparent. In this instance, I would assume that it's closer to a black or white situation is when you're talking about alpha. And then you have red, green, and blue. So you have red, so 255 would be the max, and then 0 would be the lowest, same with green and blue. And then a combination of these colors generate, the different colors you see. And I'm pretty sure in this case, black or white is the alpha level, with grays in the middle. And then the touch sensor, super easy. It's best used for user input, but also can be used as a limit switch. And we kind of use this year for inside our robot. We use this to track or check that there's a stone inside our robot, so we can auto close the claw, and then it would know that the robot can now place it. So on the control hub or expansion hub, same thing when working with the ports. You would connect it to this side. So most of these are I2C sensors. So you just plug them in with these blue, red, black, white, black cables into here, and then it's in there. You connect it via the configuration on your robot, and then just like that, you'll be able to use them straight out the box. So we're going to kind of do this now. So if you go back to your project, let's start working with our distance sensor. So we're going to create a quick linear op mode that tracks, the distance sensor and does different things based on it, as well as, teaching you how to receive data from it. So we're going to create a new class called distance sensor auton. And class is the exact same as file name. If you change this, it gets super upset. So we're going to keep that. We're going to hit extends linear op mode at autonomous and give it a name. So this name, for those that don't know, is what shows up on your driver station that you click. So while I did call it distance sensor auton, right here I'm just going to call it distance sensor program. And that's what you're going to see. And then we're just going to set up our file. So we're going to set up an override, and then we're going to do a public void run op mode. So from here, what we can do is we're going to do our basic configuration of setting up and all of that. So we're just going to set our DC motors up. So left, drive, right, drive. Then we're going to set up our distance sensor, which is pretty easy. Distance sensor, dist sensor. You can name it whatever you want. We're just going to name it like this. And we're just going to create our lapse time. It's always good to just have this in case you'll ever need to be tracking time. Just going to call it new. So right here we declared it. There's our distance sensor, our drive, and our elapsed time. And then let's also declare our power while we're at it. And you might say, oh, this is super repetitive, and it is, but until we start talking about functions and methods and classes and objects, then it's going to be really easy, and we're just going to write like 2 lines of code and all of this will be done for us. So DC motors and DC motors EX. EX is basically the extended version, so you kind of get a little bit more features, but not enough to really make a big difference. I mean, I haven't really looked into it that much, but you might get more PDIF control or PIDF control than the normal DC motors. But I haven't played around with them that much. So we're going to do hardwaremap.get, DC motor.class, left_drive, right drive equals hardwaremap.get, DC motor.class, and right drive. Then we're going to say our dist sensor. So this is basically the exact same thing. We're just going to do hardwaremap.get, distance sensor.class, and then we're going to name it dist_sensor. And then we're going to set our directions. So direction DC motor dot direction dot forward. And then we're also going to set, like always, our reverse. So right drive dot set direction DC motor dot direction dot reverse. And so right now we're actually going to add our time of flight additional features. So I'm just going to write this. So optional for TOF. So all you have to do is you're going to write rev 2m distance sensor, we're going to call it, sensor time of flight equals, and then parentheses, rev, and then distance sensor semicolon. So this is now going to create our time of flight portion. So this is now a different object than this one. So we can get some information from here and some extra information from here. And if you remember, time of flight is basically the time it takes for light to bounce off, not just how far it is or the reflection of it. We create our telemetry.add line. So add line just basically means add a string, and then add data would be, having a string with a title and then maybe some information that we're going to kind of talk about right after this, or in this file actually. So we're going to say robot ready, telemetry.update, and then wait for start. So first we're going to create 4 different variables, and they'll all be doubles that we can receive our information from our distance sensor. So the first one we're going to make is called double dist milli, or milli, and that's going to be basically equal to the distance sensor dot get distance unit. So there's multiple distance units, and we're going to grab the millimeter one. So this variable now tracks all the millimeter counts that the distance sensor can track. Next one we're going to do is dist centi, and it's basically the exact same thing. So except this one's going to get the centimeters. The autocorrect on here is super helpful in reducing how much time you actually have to spend searching for things, which is way better than what OnBot can give, which is one of the reasons I try to use this over the other. So I'm going to search through this list of items. Sensor.get distance unit meter. Okay. So all these are going to convert into the values that they track. So right here, it's going to go from super broad to super specific. So your meters is going to be, maybe it's going to be max of 2 meters, right? So maybe the max you're going to see is 2. Inches are maybe, a lot more, then centimeters a lot more, and then millimeters are the most precise. So you might need to play around with which one you want to do. Meters might be helpful if you're going a far distance away. Inches might be if you want to go, maybe a medium, centimeters, and millimeters if you want to get super precise. So now we're going to create some telemetry, and this is where we're going to use telemetry.addData, and this kind of formats it a lot better. Sorry. So first what I'm going to do is we're going to say device name, comma, and then we're going to write dist sensor dot, and then right here you can see all these different things. So we're going to do get device name. So this is one of the things you can receive from it. Next we can do telemetry dot add data. We're going to do millimeters, comma. Then what we're going to do is something called string format. And what this does, it's going to format the value we get from dist milli into something that we can, read a lot better. So right here, you're going to make %, .01f mm, and then comma dist milli, semicolon. So right here, you might not understand what string format is, but if you Google it, you'll basically be able to find out there's a lot of different ways you can format, data, and this random piece of gibberish, this %.01f, basically formats this value into something that's a lot more readable. So now we're going to do the same thing for the other variables. So telemetry add data, inches, comma, string dot format, and it's going to be the exact same. So that 0.01f cm telemetry dot add data. Oh, that should be centimeters. Centimeters. Inches, comma, string dot format. And then dist inches. Then we're going to do telemetry dot add data one more time for our meters. Oh, right here, I forgot to write IN. Okay. And I like it there. So all these that are being highlighted are all string formats right here that will format the information that we get from these. So our millimeters, our centimeters, and our inches, and then our meters. So next what we're going to do is actually get our TOF, or time of flight information. So TOF information. And so what we're going to get from this is we can get a few different values. We can get our ID from it, which you might probably not need. There's way too many things that you don't need, but we're just going to talk through most of these things. So we're going to do a string format, and we're not going to use the same one that we did last time. We're actually going to change it up. So we're going to use %x, comma, comma. Oh, I messed up a bunch of those up there. Dang it. There, that fixed it. Okay. What you want to do is make sure they're inside the string format. And then right here, we're going to do sensor time of flight, which we created right here, based on our distance sensor. And we're going to get the mode ID. And then see, there's so many different things you can do right here. Semicolon. And then we're going to get something else, which is probably more helpful. So we're going to get timeout, or did timeout. Then we are going to add a boolean because there's a true false value. So boolean dot to string sensor of time of flight dot time did occur. So if .getDistance is undefined for you, you can really just type import.com.qualcomm and it should probably autocorrect that out for you if it doesn't automatically import. Or you can just click on something and then option enter is what I have on Mac. I don't know the Windows version, probably alt enter, and you should be able to import it directly from there, and then semicolon right there. And then all the way at the end right here, we're going to create a telemetry.update. So what you really want to do is at the end of all these, it's going to update. So we have all these things, then it's going to update and basically send it. So when you update, it sends it to the driver station. So what we're going to do is actually utilize this information. So we're going to use while dist inches is greater than 5, we're going to left drive dot set power negative 0.25, so we're in reverse 25%, right drive, and at the end we're going to do left drive dot set power 0, right drive dot set power 0. I'm just going to format that really quickly. Cool. So what this does is we basically say while our inches value is greater than 5. So it says, so say we're on one side of the field and we want to track if we're on the other side, and our distance sensor is on the back of our robot facing the other wall, and we want to drive backwards until we are not greater than 5, which is going to be, under 5 inches. And so the reason we're going to run backwards is because our distance sensor is on the back. It could be on the front, but it doesn't really matter. It depends on your situation. For us, it's going to be on the back, and the robot's going to move backwards slowly. And the reason we're going to start slowly is so that way the distance sensor has more time to track the inches, the millimeters, the centimeters, and even normal meters away from the nearest, solid object, which would be that view mark at the end. And then as soon as it can find it, it'll stop. So the thing you have to realize is that if the robot's moving slowly, it's never going to be exactly 5 inches away. So you might need to do something running at super high speed and slow down super, super slow, maybe even 5%, so you can get that exact value. Because if you run too fast, the distance sensor doesn't have enough time to keep track of it, which results in this did timeout becoming true. It won't be able to, access the information that it's trying to do. How fast can the distance sensor send the data? I mean, it depends on your situation. For us, we would run, our robot would be on one side and we need to get to the other side, so we would run it down with a time super quickly, maybe across 4 tiles at 50% speed, and then with those last 2 tiles we'd run at 20% speed lowering down. If you don't have, so the amount of time of, it can respond to data, it really depends on the situation, but it's faster than you would expect. Because we used it, we were kind of, over it a little bit. We kind of used it way more than we did, and we depended on it a lot, but it was actually super helpful. Online, there have been a lot of discussions whether, odometry versus distance sensor, what is going to give you better results, and most likely odometry will, but the distance sensor is really good for new teams that want to get super accurate with position tracking on the field. So that's something to look into, and especially knowing that the view marks will be there, that is also super helpful. But you might not be able to track where you are in the field at all times based on the 2 meters. Just check. Yeah. Okay. So next we're going to actually work on our color sensor. So we're going to create another file. So Command N, Java class, color sensor autom. extends linear op mode. And then what we're going to do is just call it autonomous. It's going to be super repetitive, so we're going to kind of move a little bit faster through it. Just going to call it color sensor. DC motor, left drive. Color sensor. And that's fine because it's lowercase, not uppercase. Create our elapsed time. Then double power, 0.35. I'm going to set this one a little bit lower. We're going to add our override, public, fully run, hot mode. Left drive equals hardware map dot get DC motor dot class left underscore front right drive equals hardware map dot get DC motor dot class. And we're actually going to make a parent class a little bit later with all of our hardware mapping and all of this to reduce that. We're just going to kind of get into the process of understanding each of the code by writing it over and over again, so then when we actually finish it, it'll be super quick. So we're just going to create forMap.get. Same deal with the color sensor. That was the wrong thing. We set our left drive to the same directions that we normally use. So here's where we're going to actually start setting up our color sensor. So what we're going to do is we're going to actually turn on the LED on there, which is the little light, and then that's as simple as just writing true. So we have color sensor dot enable LED true. And so right after here, all we got to do is just say telemetry dot add line, and then we're going to do robot ready. So right here, we're going to have our update, and then we're going to do a wait for start. So now we're actually going to receive all our data from our color sensor. We're going to do telemetry.add data. We're running alpha, color sensor.alpha, telemetry.add that. Red, color sensor.red, so it's pretty easy to get this going. Blue, color sensor.blue. I skipped the G in our GB. Telemetry.add data. Green, color sensor.green. So right here, while color sensor, so this is super similar to what we had last time with our distance sensor, and this value is going to be different for where you place it. So I'm just going to set it to 20. Probably isn't the right value I need to set it to, but it's okay. So set power, and then right drive dot set power, and then we're going to set our power to 0. So we're gonna let's just talk through what this code does really quickly. So we turn on our LED. We're gonna receive our A, our R, our G, and our B. So alpha, red, green, and blue. And then we're gonna say, while our red value is less than 20, move forward. So an example of this would be needing to park. So during Skystone, you need to park on the tape in Auton, right, between the bridge. So what you could do is you could say, drive forward until you see the tape, then stop. So that way you can use this and basically be able to track it. And so that's super helpful because then you don't have to really set any time. You just gotta say, okay, go straight until you find the red. But the thing is, I feel like color should only always be set as a backup or have a backup for it. Otherwise, if it misscans for some reason, your robot's just gonna drive straight towards the wall till the end of autonomous. And you can replace this value with blue, green. You can create these into variables. So if I want to make, double of alpha equals color sensor.alpha, then you can replace that with alpha. Let's just create a variables while we're at it. Red, blue, red, green, blue. And so right here, let's just start replacing values. So red, and let's remove that. It's right here, and then all I have to say is, while red greater than 20, you can replace it with alpha, you can replace it with blue, you can replace it with green, you can really replace it with any value that we have clearly already set. So now, we're going to work on our touch sensor. And so the touch sensor is a little bit different, but we're going to kind of go through, and the touch sensor is what we're going to spend the most time with today, because we're going to actually incorporate it into our functions and methods later on when we're creating our classes and objects. So we're going to create another class, we're going to call it touch sensor auton. So we're going to really just quickly go through this. Hopefully you know by memory on how to do this. So what you might think is you might write, oh, touch sensor, yeah, this is it. But actually, what is more recommended to do is something called digital channel. And this is actually basically the exact same thing as the touch sensor. So we're just going to write digital channel, and we're just going to call it touch sensor F, and we're making another one called touch sensor B. So we're going to set one for touch sensor on the front of the robot, one for the back, and let's just create our elapsed time. Elapsed time. And then we're also going to create our double power. And this time we're actually going to set it to negative 0.35. So why are we going to set it to negative? So we're actually going to set it before. So we're actually going to create our hardware really quickly. So TCMotor.class. Get TCMotor drive. So we have those, and then for our touch sensors, the basically exact same thing. So get digital channel.class. We're going to call it touch underscore F. And remember, you can name these whatever you want. And we're going to set our directions really quickly. And we're going to set our touch sensors. So you have to actually set them to a mode. So our modes are mode dot. There's an input and an output mode. We're just going to use the input mode so we can receive information or the input from it. So when we touch it and stuff. Channel dot mode dot input. Here we're just going to add photometry. Okay, so now we're actually going to try a lot of different ways to utilize this. So first what we're going to do is we're going to say if, so we're actually make a loop so it'll just run forever. And most of the time you don't want to do this, but for this testing purpose we will. So we're going to write if touch sensor back dot get state equals true. So this means if it's touched, there's two states, a true state and a false state. So when it's pressed, it's true. When it's not pressed, it's false. And the quicker way to write this is by, let me just comment this out. So you can write that, or you can just write if touch sensor b dot get state, and it will automatically assume, yeah, true. So if it's touched, then what we're going to do is we're going to set our power will be this. And that's the exact same as writing power equals power times -1. So this multiplication equal sign basically says multiply itself by -1. And then we're also going to do, so that's our first way of doing it. So we're just going to call it option 1. And if you're going to mess with all these different options, make sure you comment the other ones out. Otherwise, they're all going to conflict. So that's option 1 and option 2. So we're going to write if touch sensor f dot get state or touch sensor b dot get state. So if either one of them are pressed, power is going to be equal to the negative version of itself. So basically the exact same of right here. The same thing, we're just going to multiplying by -1 is the same as just negating it entirely. And then we're going to have our option 3. And there's tons of ways to utilize this. We're just talking about a few of the different ways you can mess with it, because it's all about conditionals, or the if-else. If touch sensor f dot get state power equals -0.35. So it's going to go backwards if we hit the forwards one. And then otherwise, if touch sensor b dot get state power equals 0.35. So if we hit the back one, it'll move forward. This way we can just make it go in a loop. So if you put two walls between your robot where the touch sensor can hit, and you put your robot between, it'll just move between those two walls over and over again until you either stop it or the robot goes out with this third option. And even with this one right here, this one only works on the first one, but it's basically the exact same as that third option. And right here at the end, we're just going to set our power, set power to power, right drive dot set power to power. So we have, all of these now. So we have our three options, and then make sure this is going so that it loops back over and over again. So that's basically our intro to sensors. So now we're going to kind of talk about one of the more bigger parts of programming in Java as a whole. So it's going to actually be functions. So a function is a piece of code that's called by name. It can pass data to be operated on, called the parameters, and it can also give a value back to us. So this is super helpful when we're dealing with large pieces of code, like our hardware mapping, and making our variables that are complete. Like, we've been doing giant almost every single time for all 4 files we've made so far. And even this, we can break this down, and we're gonna basically break down as much as we can today into the least amount of code. So here's some examples where you might use functions. So you might use a function for encoders to, go forward, go backward, left, right. You might use functions for, time-based. So like I said, forward, backward, left turn, right turn, or even gyro to make sure that you're controlling and turning the right angles. You might use it for hardware and mapping, which is what we're going to do today, and then vision, which is really helpful for you to, have one file that does vision rather than copying and pasting the same code over and over again. And then in TeleOp, you might want to return values from the sensors, which we're going to do with the touch sensor, because writing, the get state is so long. And we're going to do hardware mapping and then as well as movement. So simply, functions allow us to use less code and be able to manipulate more with less. It's super helpful so we can minimize errors and fix issues across a larger scale. It also allows the code to be cleaner and more readable. So what now? We're actually going to go through some of our files and simplify the code using our functions. So the first thing we're going to do is we are going to simplify the autonomous that we made today into just like super easy code. So what we're going to do is we are going to, so we're going to open our file. So we have my first auton right here. We can close out some of these. Let's just close them out. And what we really want to do is we want to simplify all of this. So what we're going to do is we're going to actually hit Command or Control A, and then Command or Control C, create a new file. I'm just going to call it autonlfunc for functions, and paste that right here. Rename that to autonlfunc, and then I'm just going to call it auton with functions. So what we're going to do is we're going to consolidate this code. So how we can create a function is like this. Right here, right before this last curly brace, so this is what closes the actual class or the file, and then this is what closes our run out mode. So everything here is going to be run. So let's create, right here, we're going to write public void, and then give a name for our function. So right here, we're just going to call it forward turn, add parentheses, and then add these curly braces. And we're going to create 3 functions actually. So we're going to have forward turn, public void robot stop, and then public void move. And so these are all going to work together to make sure we can make all this code into 4 lines, or 5 lines. So first what we're going to do is we're going to work on this move. Actually, let's work on our robot stop. So we can hit this, and see how we have this? We can actually just cut this out and paste it in here. And then instead of writing that, we can just write robot stop, and then this does the exact same thing. So we've already, consolidated a little bit of it into itself. Next, let's work on move. So right here, we have our type. So void basically means we're not returning any value. So nothing's going to return out of here. It's not a variable. We're not going to receive a value from it. But what will happen is, so we're going to actually feed in information through this one. So we're going to create a double called left power, a double called right power, and something called long time. And so long is, like I said, is just like an integer, except it can hold a lot larger values, and that's what sleep is built off of. So inside here, we're just going to copy this part right here and paste it in there. So what we're going to do is we're going to match these values into here. So I'm going to write left power, right power, and time. And you can see that these light up as these are filled in. So this value will be left power, this value will be right power, and this value will be time. So if I want to replace this last part, I can replace it by writing, just type in right move and hit enter. You'll see that you need a left power. So we're going to write negative power, and then 300. And that one line does the exact same as what this does. Turn left. So we control the left motor, right motor, and then the time. But let's actually take it one step further. So here, instead of forward turn, let's combine a bunch of these. So we're going to use move, and we're going to write, so we have this. So actually, if we copy and paste this in here, paste that in there, and we actually delete all this, and write forward turn, and just, paste that 4 times. We have 4 returns, and then the robot stops. Pretty easy, right? We can run this and be perfectly fine. But let's take it, one step further. And we can do that by basically taking, we can write move power 700. And then same here, move negative power 300. And so this is the exact same as writing that. So we can delete this, we can delete that. So turn left for 0.3 seconds. And just like that, we basically consolidated most of our code into this much. And it's pretty cool. So functions allow us to do this and, make our code a lot smaller and a lot easier to manage. So let's also do this for our touch sensor. So let's open our touch sensor code. Let's create some functions right here. So we're going to actually open right here below, and we're going to create a function that returns a value. So we're going to say public void, or we're not going to write public void, we're going to write public boolean. So it returns a boolean is touched. And we're going to feed in a digital channel touch and named touch sensor. So these aren't parameters or variables we can use within our functions that don't correspond to anything outside. So what we're going to do is we're going to write if touch sensor dot get state. So if the touch sensor is pressed, return true. So we write return and it returns a value. So, but why is it still upset? It's because only if it's true. Well, what if it's not true? What if you're not being pressed? Then we're going to write return false. And just like that, we have this much done. So here what we can do is rather than write get state, we can actually just write touch is touched, touch sensor B. And then it allows it to be a lot more readable. And we can actually just, go in here, F, do that. And so while this doesn't seem that big of a change, it actually allows us to do a lot more complex things because we can add in more different types of features into it. So if we say if the front and back are both being pressed, do this. So right there, we've already replaced most of these functions. So let's try something else. Let's create another return function. So public double mod power, and that's just going to stand for modified power. And we're not going to feed in any parameters this time. We're just going to say we're going to create a variable, and this variable is going to be called mod power. But this variable, if I type it right here, I can say mod power, it turns red because the variables created inside functions only exist within themselves. So you write equals power, and we can do this because power is actually outside of this function multiplied by 0.85. So we can do that, and we can write return mod power. But we can also just simplify this even further. We can just write return power times 0.85. And if we wanted to feed in a value, so we can say double in pow, we can write in pow. So when can we do this? We can write right here, we can write in, we can write mod power, power. So this isn't that helpful, but it just shows you that you can do these types of things where you can actually manipulate values. And I can change this to maybe 1, and it would give me 85 back, or 0.85 back, because 1 times 0.85 is, that. So it's basically doing that, if that sounded weird. And we have this in the end. So that was kind of a quick intro to functions. There's a lot of different things you can do with that, and we're going to kind of dive in a lot more into that when we're dealing with creating our objects today. So what really is the point? So the whole point of functions is to not write repetitive code and keep our code base to a low line and character count. So we'll ensure that everything is more organized and easier to write. Next, we're going to be going over object creation for something called modular code. And this allows us to use the same code in multiple areas by just writing one line. So modular code comes from creating object files that you can use within your op modes. And we're going to be creating 2 of them, robot and movement. So last week, we kind of looked at the definition of Java. And we're going to kind of reiterate that one more time. So Java is a general purpose programming language that's class-based, object-oriented, and designed to have as few implementation dependencies as possible. So today we're going to kind of talk about the class-based portion and object-oriented. And then next we're going to kind of dive into polymorphism and hierarchy of these classes. And you might not understand what that means, and I don't expect you to, but we're going to kind of dive in a little bit today and then go a lot more in next week. So what is an object? Objects have both states and behaviors. So for example, a car has states as color, type, brand, as well as behavior, starting, stopping, playing music. An object is an instance of a class. States are information that is unique to the object, while behaviors are more like actions of the object. So let's compare two cars. Let's compare a Tesla and an Audi. So the Tesla, let's get a red Tesla Model 3. So it's a red color, the type is a Model 3, and the brand is a Tesla. States. Our Audi, however, might be an Audi A4 that is gray or silver, and the brand is Audi. So we have two things, they have different states. However, the behaviors, starting, stopping, and playing music, are the same for both. So that kind of gives you a good instance on, the differences between objects. So objects can be very specific. So states are information that are unique to the object, while behaviors are more like actions of the objects. In the whole object-oriented system, otherwise known as OOP, or object-oriented programming, is basically based on the real world. You have a lot of objects. You're probably on your computer right now, and everyone's computer is probably different in a way. So that might be, the state. But they all do the same thing. They all might, go to Chrome. They all might, program, watch YouTube, Netflix. So all these different types of things. And what is a class? So a class is the template or blueprint that describes the behavior or state that the object of its type supports. This allows objects to manipulate the methods of a class. So, the class might be car, and then it's a template for, our states and behaviors. And these behaviors might be changed. We did say that they might be the same, but as you know, the Tesla is an electric car, so it has automatic acceleration, versus the Audi, which is a gas. We're talking about e-tron, but not in this case. We have, it's a gas car, so it might not have all the features that the Tesla may have. So that's, some of the more influences the state might have on a behavior. So like I said, the class is a template or blueprint that describes the behavior or state that the object of its type supports. So this allows objects to manipulate the methods of a class. So you see me throw around two different terms here. We have methods and functions, and I've kind of used them interchangeably, which isn't that good, but it doesn't really matter at the same time. Methods and functions are the same, but they have different names or different terms. Methods are functions in your classes, which is involved in OOP, or object-oriented programming, as I said, and functions are groups of reusable code that being called anywhere. They are the same, but it's very easy to get the terms mixed up. So you can say functions in an object, which is a method, or functions outside of the object, which is a function. So it's super easy to get them mixed up, but they're essentially the exact same. So we're going to be creating two classes today that we can create objects based off from. We're going to be creating a class for our hardware, and then a class for our movement. One's going to be called robot, and it's going to have hardware variable calls, hardware mapping, and they're going to be dealing with movement, and potentially our encoder code that we might get to if we have time today. Yeah, okay. So what we're going to do is we're going to create a new Java class, like we've always been doing for all our other files. We're just going to name it robot. So we're just going to leave it like this, and let's just start, declaring some of our variables in here. So we're going to write DC motor, left drive, right drive, and arm motor. Next, we're just going to create our public, and make sure what we're going to do is we're going to do something called public. So public means that when we use this object outside, we're going to use it outside of this file, we'll be able to access it. If it's private, we won't be able to access it. So you can change it to private, and we won't have access. But public allows us to manipulate these outside of the object. We're going to create another public servo named class servo. We're going to create a public elapsed time named runtime. And then we're going to set some variables. So we're going to create two variables for our power and our servo position. So let's create our power first. We're going to write public. So declaring a method outside of a class. We're going to actually talk about that as soon as we finish building our class. You don't have to feel dumb. So we're going to have public static final double power equals 0.85. So we're going to talk about what each of these, what keywords mean. So public, you've already went over that. It means we can call it outside of this object when it's being called. Static basically means it belongs to this class and it's going to be the same for all instances and it can be manipulated for all the creations of the object. It doesn't really matter for us in this instance because we're just going to have one robot class. We're not going to be creating multiple in the same file. And then final basically says it can't be changed. Like this value won't be changed for now. And then in our double, it's just saying what type of variable it is. And we're also going to create another one. So let's create another one. So public static final double servo position equals 0.45. And the same thing, static can be accessible for all instances of the class, manipulated for all, and it belongs to this robot class. Final can't be changed. Public, you can access it out of it. And so now we're going to do something called create the constructor, and all objects require this. So public robot parentheses and then add these. So what this does is it prepares our object for use when it's called, and it accepts arguments which are very similar to parameters that the constructor will use to set variables. And so we won't really mess with the constructor now, but we will when we create our movement class. So first, let's create our first method inside here that initializes all of our hardware for us. So we're going to public void init and then semicolon. So what we're going to do is let's just type in our normal code. So left drive equals hardware map dot get DC motor dot class left underscore drive. Right drive equals hardware map dot get DC motor dot class right underscore drive. Arm motor equals hardware map dot get DC motor dot class arm underscore motor. And then we're going to do our servo. So claw servo equals hardware map dot get DC motor, not a DC motor, it's a servo dot class claw underscore servo. So what you can see is that hardware map is red, and the reason why is because hardware map belongs to linear op mode, but this isn't an op mode. So how do we send in this value? So what we're going to do is we're going to create a parameter for this. So we're going to write hardware map, and we're just going to call it HW map. And so now we can actually just replace all these, and now it's all resolved. And basically, since it's not a linear op mode, we don't have access to this. So what we're going to do next is we're just going to do some of our direction setting in our telemetry. So we're going to say left drive dot set direction DC motor dot direction dot forward, right drive dot set direction DC motor dot direction dot reverse. And then let's add our telemetry. So telemetry dot add line robot ready telemetry dot update. And the same thing is happening again. So what we could do is we can do the exact same thing. We're going to add comma, so we can add another parameter. We call it telemetry, and we're just going to name it telemetry. So it doesn't matter. We could have definitely called our hardware map, but HW map, same thing, gets the job done. So now what we're going to do is we've made our first object. So now let's actually start integrating this. So I'm going to take this code, copy and paste it, copy it, create a new file. We're going to call it TeleOp. Just going to paste it in here. TeleOp. So watch me. I'm just going to delete all of that. Delete all of that. And I'll keep all of this for now. So what I'm going to do is I'm just going to type robot equals new robot. So this is super similar to how we actually created our elapsed time. So we're creating a robot object named robot. So what can we do now? So we're going to write robot dot and we can access it, init, hardware map, telemetry. So to basically pull our method from this class, or this object that we created, we just have to write .init, and that we created that right here. Let me close out some of these. Right, we created this, we have our init right here. And we have this, but we're getting errors everywhere else. So let's actually fix that as well. So I should have kept my wait for start. So see how this runtime is becoming, red? But we want to use the runtime from here. So let's actually type in op mode. We're going to do robot.runtime. If I just typed in robot dot, you can see that we have access to each motor, our servo, runtime, our init function. So actually we can do that for the rest of this. So we do robot.clawServo. We can do robot.clawServo right here. Robot.left. Robot.right. Robot.armMotor. Robot.runtime. And robot.servoPosition. And just like that, all of our errors have been fixed. Except for this. What is it getting upset about? Oh, forgot the lowercase p. There we go. So just like that, we were able to take, our code that looked like this and convert it to that. So, from 69 lines to 47 lines, we fix that. And you can even consolidate this even more than we did. And we did call our init function. So let's also add this to our TeleOp. So let's create another class. Auton. We're gonna grab this. Not that one, this one. And the same thing can happen. So, auton. So auton with oop. So we can remove all of this. We can just write robot equals new robot. It sounds super redundant. You can change this middle robot to whatever you really want, but I'm just gonna say robot for now. We can remove all that. So robot.init. Remember, we're gonna insert our telemetry and hardware map because they're variables from our linear op mode that aren't given access into there. And so we have all this right here. We can, remove that. Let's grab the one from our functions that we created. So we just grab this. There. And right here, we can just do robot dot for every one of these red variables. And then just like that, we have all of our things set. So let's create our second object now. So our second object is going to be a movement function that we can store all of these within. So we're going to create another object. We're going to call it movement. So we're going to write robot equals null, because we want to get the information from our robot object. We're also going to write linear op mode equals null. And so these are going to be our arguments. So like I said, we already have access. We wrote our constructor right here. And remember, what the constructor does is it prepares the object for use and then accepts the arguments that the constructor uses to set new variables. So what we're going to do is we're going to set movement right here. We're going to set public void movement, or not even that, just movement. And then inside of here, we're actually going to declare our two variables. So we're going to do robot equals a robot, and then op mode equals a op mode. And these are coming up red, so I have to feed them in through here. So we're going to say robot, a robot, linear op mode. And you can change that for your iterative as well, but we're just going to focus on linear for now. And boom, just like that, we can feed in now information and receive it from our robot as well as the overall arching linear op mode. So let's also create some variables. So we're going to say we're going to create a variable called power, and we're going to set it equal to robot.power. So that's going to be the same as writing it 0.85. And we're also going to we're actually going to move in all of our functions from here. So we can actually copy these. They turn red. And then we have this. So all these work, they all have robot dot, except here for the sleep, we're going to have to write op mode dot sleep. But we're getting errors here now. So how do we actually integrate our movement function, or our movement, class, and make an object out of it? So we're going to do the same thing that we do right here. Movement move equals new movement. And it's getting upset. It wants 2 arguments. So we're going to set robot, comma, this. And why do we write this? So this is basically saying this file is an op mode. It extends linear op mode. It is basically a child of linear op mode. So when we're looking for an op mode to use, we're just going to write this. So all these are still red. So we're going to write move dot, and look at that, all just fixes itself. And that's pretty cool. So we can actually kind of dive in a little bit more. So let's take our, our touch sensor Auton and combine some of the functions we used here with our robot. So what we can do is we can just copy these 2. Those are going to give us errors. We can paste that down here. It wants, some information. So let's also give in our digital channels. Right there. And let's delete that. Delete. We can add these things into our init. Delete. And delete all that. And then right here, we have these. All these errors are coming up. So what we can do is we're going to actually set a double of power. Actually, let's not do that yet. We're going to create our robot equals new robot. And we don't even need our move, but we can add one in. So actually, we don't even need to. We'll just use their robot. We're going to write robot.init, hardware map telemetry. And so we have all this now. So then we can just write robot.isTouched. And then just like that, we can call in all these other things. So we're just trying to simplify how our code is being written. And we can even go fix some of that later. So we have this power variable. But what I want to do is, since the other one's static and we can't change it, let's just create another one called double power equals robot.power. And now all of this is fixed. Same thing like we did right here. So let's take this part and add that to our move. So we're going to take movement move equals new movement robot comma this semicolon. So you can actually just go into movement. Let's create, we already have a move right here. But what we're going to do is we're going to create another one. So we can actually take this, repaste it one more time, and then remove the sleep from it. So this is something called overloading. And overloading means is we can keep functions with the same names, but the different number of parameters. So this only has 2. We only want left power and right power. This one wants left power, right power, and long time. But what we can also do is even compile it even further. So we write move, and then we can just write left power and right power. And so this is a really cool part of overloading, is that we can actually take this one function, integrate it into this function, which then controls other functions in the process. So right here, rather than writing this, I can just write move dot move. Then we can set robot dot mod power robot power. That. comma, move dot, and yeah, and then robot dot mod power, and just like that, we're controlling both left and right. So we can just comment this out. But let's actually take it even further. We can actually just add one parameter. So we can write public void move power double power, and then we can write move power comma power, and then here just delete that. So we compiled this much down into this one small piece of code. So let's kind of work our way back into how we did that. So we created a function called move right here. And so move with one power means that both motors will move the exact same power. This other move with two parameters means that it will run forever with controlling each power of each wheel. And then this one right here with 3 means we can control how long it runs. For both of these will run unlimited because there's no sleep attached to them, versus this one, which does have a time attached to it. Just gonna format this a little bit. And you can even go even further by taking this TeleOp. You can even just move all of these out into your movement function if you want to have multiple TeleOps. But the reason object and class becomes so helpful is because we can create super short pieces of code like that. Like that is short, and it does all the same things that does all the same things that this code does. So that's pretty helpful. So that's why objects are super important and helpful for you to work with. So now we're going to kind of dive in to our next topic, which is encoders. And so we are getting pretty close. We're going to end around 10 minutes, 13 minutes-ish. And we probably will have to finish this up next week, along with the rest of our content. But we're going to kind of go through it just a little bit. So what are encoders? So inside a motor, there is a little magnet on the end, which connects to a shaft inside the motor. And the shaft is usually what you put your gearing onto, your wheels. So this magnet is the encoder. It basically tracks tick values, or how many rotations that the shaft is going around. And it returns tick values, and we can give it tick values to run to. So if you're looking at your expansion or control hub, you'll have on the rev side, you'll have a core hex motor, and then you'll have your normal core or normal hex. Yeah, pretty sure it's just normal hex. And basically you have your power, which is the black and red, going into here, just like here, black and red for power. And then you have your red, white, blue, black cable, which is the encoder, going from here into this other little port, and here into the other little port. Past season, there was a lot of motors that had faulty encoders in them. So what teams had to do if you had faulty encoders, you have to open up the back of it and then move the magnet around. And if the magnet you should be able to slip a piece of paper under there, in and out super clean, but anything else bigger, in order to know that the magnet was super close to the tracking of it. So that was one way that you can fix it and get more accurate counts. So how do we program them? So for this, before we program it, we're actually going to outline our steps and then go into it and understanding how they work. Because understanding how encoders work is a very important aspect of it before you dive in to actually programming them straight on. So we have 5 steps. First, we're going to tell the robot that we want to use encoders. This basically says, okay, robot, I want to use encoders, not just, my time. Give me all the extra features that encoders give me. Then we want to give a tick count value. And we're going to do something called inches times ticks per inch to figure this out. Then we're going to give our motors a power. Because the great thing about encoders is you can run distances across various powers, and it should be the exact same distance. Then we're going to run the power and wait. until we're done running. And then we're going to turn off the motor's power and say we're going to run to position. What this means is it's actually it's basically a command we can give to our motor, and it'll understand it when we kind of get to that point. So the first part is that we're going to tell the robot that we want to use encoders. And this part's pretty easy. For this example, we're going to be focusing on a 2-meter drive, but you can adapt this to other drivetrains. And just like we learned objects today and functions and methods and classes, so then we can make sure that our code will be super easy and clean to read for this part. So we're going to do robot.leftMotor.setMode run using encoder, and then same for our right motor, or left drive, right drive, same difference. And it's super adaptable for other drivetrains. So this year we use it on Mecanum, and it's helpful for Mecanum. Mecanum slips, so you need more gyro, control to fix that out and make sure that the angles are all solved. Number 2, we're going to give a tick count value. And so what this means is that we're going to tell it, here's our tick count, figure it out, now go this many ticks. So finding a tick count value is specific for your robot, so there's not really a precise value that we can give you that will work. However, when we're trying to find a really good tick to inch value that we have to just get like all of a sudden without doing any math behind it or figuring out our gear ratios and all that, they just want to be a quick answer. We use a TeleOp that will allow us to manually track the ticks per inch, and you can get pretty close to the correct number using this method. So if you run this, you can move the robot manually and get values back. And I'll kind of show you how that program works right now. And then we're going to do something called float, which is not the variable type, something different. That means at 0 power, your wheels will spin. So what we're going to do is you put your robot on the ground, you turn this program on, and you can have your hands on the robot and move it around against maybe a ruler or a yardstick or something, and basically track the distance it takes and how many ticks you're receiving. So if you go to the site, stempump.com/r/getencoders, it'll link you to a GitHub page for this file. So let's just go there. So we just type that in. It's the link right here. So it's a very basic file. We have it's a teleop, it extends linear op mode, we have our robot basically initialized, and we set something called 0 power behavior. So there's multiple types of this. The one we're focusing on right now is called float, and basically what that means is when the robot's at 0 power, the wheels still spin freely. And most of the time you don't want this. You want it to be able to stop, but this is helpful when you want to have a little bit of a drift to your robot. And then we'll talk about set encoders when we create that function, hopefully today or probably next week. And then right here, we're basically getting our current positions from our left drive and right drive, and it's updating it live. So you can actually receive data from here. So that's stempump.com/r/getencoders. Step 3, we're going to give the motors a power. So the whole idea behind encoders is that they go the same distance on any power. This is why using encoders is always more accurate than using time-based autonomous programs. They're just a little bit more complex. To give power to motors, we just have to do this. Robot.leftMotor, or left drive, .set power, then parentheses math.abs speed, and then robot.rightMotor.set power math.abs speed. So what math.abs does is something called absolute value. And absolute value basically says if the value is negative, make it positive. If it's positive, stays positive. And that's really helpful because when you're dealing with encoders, you only want to deal with positive power. But we did talk about, reversing the power makes it go in the opposite direction. So how would I do that on here? And so the difference for encoders is that you would use negative distance rather than using negative power. This way, it's a lot more accurate versus using just power to go the same distance backwards. And so, like I said, there's a reason we took the absolute value, and that just converts any value that we feed into it to a positive value. This ensures that no matter what, power is always positive. If you want to drive backwards, give the encoders negative distance. When we then have to make sure that power is only being given when the motors are busy and the op mode is active. Otherwise, the loop won't run, because this is all done inside a big while loop. So step 4, we're going to wait until our motors are done running. So right here we have a while loop that only runs if all these conditions are true. So if our op mode is active, so if our program is running, if robot.left motor is busy, so it basically says if the motor is running, and then if the right one is running. So see how there's parentheses right here and here? So that's basically saying both the motors have to be running and this. So if one of these is not working, the entire thing goes out. The entire loop stops. And that might be helpful because maybe you're tracking, both motors are always running at the same times for the same distance, so you don't really have to worry about that. But if you need them to be running, you only want to track either one of them being busy, then you'd use the OR, which is the 2 lines, which is on top of the backslash under your backspace key most of the time. And then you can control if only one of them is active. So inside this while loop, we're checking that power only runs until the encoder ticks are met. And in step 5, after this loop, we're going to set our power to 0, and we reset back to run using encoders. Robot.leftDrive.setMode, and then we're going to reset back to this. This basically tells it to stop. So what we're going to do is we're going to combine all of our steps into a method that allows us to drive our robot using encoders. And today, since we're almost getting done in a few minutes here, we're actually only going to do a very minimal amount. So we're actually just going to open our robot.java file and create our set encoders function. And this will be super easy. So we're just going to write public void set encoders left drive dot set mode DC motor dot run mode dot run using encoder. The same thing, we're just gonna copy that. We're gonna paste it, write drive, and just like that. So also right now, what we can do is we can either add that into our init, or we can just call it directly. And the reason we're not going to call it, we're going to call it directly over init is because we use this init in TeleOp, we use it in multiple areas. So what we're going to do is we're going to create a file called Encoder Auton right now, so we can actually test this out. So Java Encoder Auton extends linear op mode, autonomous name encoder Auton override public void run op mode. So we're going to create some variables right here. Robot equals new robot. Movement move equals new movement. And like I said, since we're running out of time here, we're not going to really dive into much other than getting this file set up, and then we're going to be finished for today. Robot, this. Robot.init, hardware map, telemetry. And then right here, we're going to do robot.set encoders. And then we're just going to get our wait for start running. Wait for start. And then right here, we'll set robot, or is it move? Yeah, it's a move.robot stop. And then I'm just going to add a comment here for encoder movement. So that about wraps it up for today. If you didn't finish any of the things that we've done today, you can go to stempump.com/r/FTC for a written version, and you can actually follow there, and it matches the exact same schedule and curriculum that we're following right now. And if you find any errors there, you can always just send us a message. So this is the second camp that we've done for FTC programming, and then next week is the third and last one. Last week we finished web design. So this Thursday we are hosting Python from 3 to 5 CST. Friday we're doing FTC judging from 3 to 4 CST, and that's going to run for 3 weeks as well. We're going to do Figma next week, which is a great design tool, next Thursday. And then we also have FTC judging next week as well as FTC programming. The week after we're starting Inventor, which will go for 3 weeks just like this class does, at the same time as this one. We're going to do RPG Maker, we're going to make a cool game in 2 hours. We have Java, so if you're not understanding some of the things here, that course is going to be really helpful for you. So it kind of takes out all the robotics stuff that we've been talking about, and only focuses on the language itself. So maybe if you're getting confused now, this might be helpful for you to go to, and it's going to talk you this, and then you can watch the videos or contact us. What is this? That's weird. There. Okay. So we have Java. If you didn't understand what was going on today, that might be helpful. Otherwise, watching the videos that we have. And then on July 2nd, we have Intro to Artificial Intelligence, which is going to be a really fun class. We're going to talk about AI and machine learning, and then the usages of it. And then we're going to actually make our own machine learning and artificial intelligence program. You can sign up for these at stempump.com/camps, or just go to the QR code right here. These are the camps. And then you can also download our app on the App Store, and you can also watch our online camps through the app, or even read any of our courses down. So you can scan the QR code here, or download in the App Store just by searching STEMpump. You can find a video of this camp and other camps that we have done in the past week on our YouTube channel just by going to stempump.com/r/YT. That's stempump.com/r/YT. And we're also going to be posting the virtual robot program on this YouTube channel as well, because it doesn't really fit into what we're doing right now. But you can find out how to get that working for over the summer that you want to test some of these programs out on. Add us on social media. We're on Discord, stempump.com/r/Discord. And you can chat with us. We'll be able to help, have fun. We have our Instagram at STEMpump, and then we have our Twitter at STEMpumpTX, and we're most likely to respond. You can find out the latest information about all of our programs on here. But otherwise, yeah, we'd love to hear your feedback on today's camp. I feel like it went a lot more smoother than it did last week's. So we're trying to still find our groove of it, but we'd love to hear your feedback about this. So scan the QR code or go to stempump.com/feedback. And otherwise, thank you for joining the stream. I hope to see you guys at other camps or next week.